Okay, good morning to everyone. A good news for you. Later we will discuss the quiz. Another good news is the average is about 19.4. So I think more than half is about 20 and above. So I think this is a strong cohort, a strong group. So those who are weaker, I think you should work hard. Otherwise, the result I don't think is easy to scale. So you have to work hard in this course. Okay, later we in the last hour we will discuss about the quiz. Okay, before we start, any question you want me to do? Yeah. You mean determinant? Okay, you mean is it only that square matrix has determinant? Determinant is defined. Yeah, determinant is only defined on n by n. I think 3 blue, 1 brown has some geometric uh intuition about that. I mean the YouTube link I put on. I think he did mention that why if it's not square then determinant doesn't make sense. I think it's about the transformation between the sense space. If it is different space, then you might be not onto, not 1 to 1, something like that. So the determinant has no meaning there. Determinant should represent something about area change after the linear transformation by that matrix. Yeah, so determinant only defined on n by n matrix, square matrix. Any other question? Liu Xing, where is Liu Xing? Liu Xing. You got a question? Huh? Huh? After class? Okay. What the others? Is Zhao Zixuan here? Zhao Zixuan? Oh, yeah, Zhao Zixuan. So you were not in Moodle previously, right? Did you notice that? How do you get those notes? Oh, from your friends, okay. Yeah, you should let me know. I just found out yesterday. Because the number keep changing, so I don't know who haven't enrolled. Okay. Yeah, should let me know next time if you are not in the mood. All right. Let's dive into today's content. Okay. Let's revisit some theorem that we missed yesterday. So let's start from something we know first. Okay, what did we learn about an square matrix that is invertible? Okay, what's the very first condition we know? When is a square matrix invertible? Remember? What's the very first one? Reduced echelon form? What about? Okay. So it can be raw reduced to it is row equivalent to identity a identity matrix. Okay, so every invertible square matrix can be row reduced to identity matrix as a REF row reduced echelon form, which is an identity matrix. Okay, why? Because this is exactly how you find the A inverse, right? It's the composite of elementary matrix that row reduce A. So let me name it A. Okay, remember? Do you remember? Okay. Next, yesterday, what did we learn? Determinant. So this is also equivalent to that the determinant of A is non-zero. Okay. So from here, you can have further more condition here. Okay. So if the determinant of A is non-zero, that means the columns of A form a basis of Rn, right? In particular, you can see it from here because it is row equivalent to the identity matrix. So every row is after reduce, every row is a pivot column. So if it's a pivot column, then it span and then it they are linearly independent. So the column from the original matrix form a basis because they are linearly independent and span. Okay. If it is span, so co A equal to Rn because you have n columns because n by n matrix. After you row reduce, you have n columns. This n to 0, n to O is immediate, right? Is it immediate? Rank of A is what? Dimension of co A. So dimension of Rn is what? N. Okay. Because there are n basis factors, right? Okay. So let me write something because of Rn or co A has n basis. Okay. M because you have n pivot column. The columns A and Rn. Okay. O to P dimension now space A is equal to 0 because from the rank theorem, right? The rank theorem, what do you get? Dimension theorem, what do you get? You get rank A plus dimension of now A is equal to n. Okay. But since rank n is n, so dimension of now A is 0. Okay, sorry. So the dimension of A is 0. Okay. So if the dimension of now A is 0, then now A is just a singleton set containing 0 vector because there's nothing in there, just 0. Only 0 that satisfy A 0 equal 0. Okay. And it is dimension 0. So there's only 0 vector in there. Okay. So these are easy consequence from these two that we have seen before. Okay. Up to now, any question? No. Okay. Okay. Next, about this theorem basis, I think a little bit yesterday. So yesterday we kind of skipped this. I want you to go back and think about this. I'm not sure how many of you got wonder about this theorem here. So let me restate the theorem. The basis theorem states that if H is an p-dimensional subspace of Rn, what does this mean? This means that this subspace has a basis consisting p vectors. Okay. So let us spell out what this means. So it has basis consisting p vectors. Okay. And then the claim, there are two claims here. So any linearly independent set of exactly p elements in H is a basis of H. Okay. Second, any set of p elements of H that spans H is a basis of H. Okay, let's try and see why. Okay. Just use some simple argument here. So any linearly independent set of exactly p elements in H is a basis of H. So you are already linearly independent. What else do you need? What else do you need to be a basis? What's the two things that you need to become a basis? What's the two things you need? Your attendance? No, no, this is mine. Oh. All right. Yeah. So what's the two properties that you need such that the set of vectors become a basis? Linearly independent and what? Span. Okay. So in the first condition here, you have linearly independent. Okay. How about span? Okay. How to see that it's span? Okay. So like this, there's not much condition on the theorem from the theorem. So suppose the p vectors v1, v2 up to vp don't span. Okay. Suppose it doesn't span and see what happens. If it doesn't span, this means there exists another vector, extra vector, call it vp plus 1. There's this vp plus 1 such that vp plus 1 is not a linear combination of the previous vector. Does it make sense? Okay. Suppose it doesn't span. So that means you have one vector that cannot write in terms of those vectors. Right? Okay. So here we got a contradiction here already. Okay. So this means the dimension of H is greater or equal to p plus 1 because you already have p plus 1 linearly independent vectors here. Okay. But H is of dimension p. Okay. So there's a contradiction. Okay. So contradiction here, so we are done. Okay. Okay. How about the next one? The second part. You have any set of p elements of H that span H is a basis. So now you already know that it spans. So what condition you need still need? Span and what's the other condition you need for vectors to be a basis? Span and what? Linearly independent. Okay, so now you need to show that these vectors are linearly independent. Okay, so how to show these vectors are linearly independent? Okay, so how to show that these vectors are linearly independent? So suppose the P vectors are not linearly independent again. Okay, are not linearly independent. Okay, for this kind of short theorem, right? Not enough information, so we cannot do something constructive. So we usually use contradiction. So suppose that they are not. Okay, let's see anything's go wrong or not. Okay, if they are not linearly independent, that's mean what? What's the definition of linearly independent? That means the vector equation C1 V1, put some arrow on, plus C2 V2 plus up to VP CP VP equals 0 has non-trivial solution. Okay, so some of the CIs are non-zero. What does it mean by some of the CI is non-zero? For example, C1 V1 plus C2 V2 equals 0, for example. So what do you get? You can write one vectors in terms of the others. Okay, right? So, so, so what does this mean? They are not linear independent. Yeah. So how this goes? As a non-trivial solution. Any idea? Any contradiction that we can make? Okay, the original plane is to contradict that it doesn't span H. Okay, I think we can. Let's see. I think we move this up. Okay, so that's means what? That means a subset of V1 up to VP span H, or a proper subset. Okay, so that means you need to throw away some vector. You can throw away some vector, but the vector still span H, right? Okay, make sense? Okay, but this means what? Means the dimension of H is less than equal to is strictly less than P. Okay, because you can use uh use less than P vectors to span H. Okay, so this means the dimension of H is less than P, which is a contradiction. Contradicts that dimension. It's P. It's P. Okay, so the idea, so why is this two theorem here kind of important? Because if I hand you a subspace, okay, you try to find a basis. Okay? You try to find a basis. So what you can do is you can start with linearly independent set. So you try to add more and more linearly independent vectors. But when do you know you want to stop? If you know the dimension of the H, then you know that you will stop at the number P. Okay, you will stop after you obtain P linearly independent set. Okay, but if you start with spanning set, okay, if you start with a spanning set, start with a set of vectors that you think that they can express every vector in the subspace. Okay, you should reduce that set until P vectors, which is the number of the which is the dimension of the subspace. Okay, but we will see similar theorem in the next chapter. Again, next chapter we will be generalizing vector space, not just Rn but different vector space. Okay, up to now, is it making sense? Making sense? Any question? Question from the back? No. Okay. No. So next, let's go to today's content. So today's we will deal with only Cramer's rule, but not volume and the rest. So this one will get real. Real. Still want to say if you are interested with the determinant being an area, you can go and watch the 3 Blue 1 Brown YouTuber. Okay, I put the link on the Moodle already. It is animated, so you can see how the picture changes. Okay, so Cramer's rule is a path before we go to finding an inverse. Okay, so Cramer's rule state like this. So if you start with an invertible n by n matrix, so a square matrix, okay, only square matrix is invertible, by the way. A solution of the linear system Ax equal to B is given by xi equal to determinant of aib over determinant of A. Okay. Where aib was aib is the matrix obtained by A by replacing the I column with the vector B. Okay. So at first I saw this rule here or the theorem here quite surprising. Okay. Because what? Yeah, quite surprising because you can find the solution using the determinant. At least for me, I'm not sure for you, but for me, it's quite surprising. So I wanted to know why is it true. So let's see the proof. Why is it true? And then we will see how to use it later. Okay, let's see why is it true. Let's see why is it true. So suppose let's start with A, breaking it into column vectors as usual. Okay. Let's see why is this true. So an identity matrix EI, E2, up to EN. Okay. So there's one magic thing is aside. Let's look at what is AIX bar. So let's look at what is this first. Okay. So maybe this is a bit too large to imagine. Let's restrict ourselves to the 3 by 3 case. Okay. So everything you see with this up to n, right? You can fix at one end and then see what's going on. Okay. So in this case, let's restrict ourselves to 3 by 3 case and then see what's going on. And then we try and look at A1 first. Okay. I1 of X is what? Okay. This is following the notation here. Okay. It's a matrix obtained from A by replacing the column I by the vector B. Okay. So now we're replacing the identity matrix, the first column of the identity matrix with the X vector here. So let's see what's this. So what we will get is x1, x2, x3, 0, 1, 0, 0, 0, 1. Okay. And what's the determinant of this guy, A1x? Anyone know how to compute this? Remember? Huh? Anyone still remember how to compute this? Determinant of this matrix here. X1. Why? Yeah. Huh? What? Yes. So because this is a, since ix I1x is a triangular matrix, the determinant is just the product of the diagonal. Okay, so this read out the x1 actually. Okay. How about let's play around with this this AI thingy. So let's do it a let's do it on I2. Okay, so let us insert the vector into the second column. Let's see what's going on. Okay, how about this? So what's the determinant of A2x? What's the determinant of this? What's the determinant of this? Any idea? This is not an obvious triangular matrix, but yeah. Why? How to compute? Okay. I'm not sure what you're drawing, but okay. So how you compute it? You can use cofactor expansion. Okay. Because using cofactor expansion meaning you can do it any row, any column you like. Okay. But this obvious easiest column that you can pick. Right. You can pick along first column or the last column. Okay. So let's say if you pick from the first column, okay. So what do you get? You have a grid plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay. So if you start with this plus, then you have a 1 times the minor. What's the minor in this case? X2, 0, x3, and 1. And now this is a triangular matrix now. Then you can use product of diagonal entries. Okay, to get 1 times x2. Okay, so in general, for n by n cases, you can use the similar argument to see that actually the determinant of I, the determinant of I, yeah, IIX will read out XI. Okay, so this is how XI appear in this determinant story. Okay, from here, let's see how we put these things together and then try to find this XI here. Okay, up to now, okay. So far so good. Okay, so now we realize xi as determinant of some matrix already. So let's move this thing away. Okay. Okay, let's move this away. So let's come back to here. Okay. One matrix you can look at is A times AIX. Okay. So what does this going on? So first of all, it's A, it's AIX. This is what we learned just now. So you replace the I column with X and then keep the rest. Okay, and then what's going on next? And then we learn from matrix multiplication. A times the column vector will be A times the first column vectors, and then for all the columns vector. And then what is AEI? AEI. A times the A, A, wait, A times the first standard basis. You will read out the first column, right? You will read out the first column. Make sense? Okay, this is how we find the linear transformation, right? The standard matrix for linear transformation. We let it add on the standard basis and then read out the columns of A. So this one will return to the column vector of A, and then AX you will get is, what is AX? This is the equation that you want, matrix equation. So this one will get you B, and then the rest is still the column vector from A. Okay, so you replace the I column with B now. Okay, and then what you will do is, okay, so this is what? This is actually AIB. Okay, is the matrix of A where the ith column replaced by B. All right, this is exactly what is this thing here. Okay, so we already retrieved this AIB here, and then we relate it to A and AI. Okay, so now you want determinant of AIB. So let's apply determinant on both sides. So we get determinant of A times AIX equals to determinant of AI. Okay, so you can see that there's two matrix applied here. Okay, because determinant is multiplicative, so we can split the determinant into the matrix multiplication. So since determinant is multiplicative, determinant of A times determinant of AIX is equal to determinant of AIB. Okay, so just now we already discussed that determinant of AIX is equal to XI. Okay, so this part is equal to XI, and then I divide both sides with determinant of A, then I will find my I. Okay, so this is the proof, and then yeah, is everyone following? Following? Following or not? Everyone following or not? Okay, okay. Please ask if you have any question. Okay. All right. Yeah. So this is one way to do this. To find. So today we meet a new way to find the solution, not by using the what augmented matrix. Okay, but Cramer's rule. So depend on which one is easier, you can pick your poison. Okay. Okay, so let's try and use this Cramer's rule to solve the linear system. Okay, let's do one together, and then later I will let you try. So use Cramer's rule to solve the linear system here. So from this linear system, I think in your mind you should automatically transform this to matrix equation. Okay. Please let me know if you still don't know how to do this. Okay. Okay, so we got an AX equal to B. Yeah. Cramer's rule need A to be invertible. Okay. Should we check that A is invertible or not first? So what's the determinant of A? What's the determinant of A? Huh? Where? What's the determinant of A? 15. Good. 15. Yes. So 15 is non-zero. Okay. So non-zero, then from the first thing we said in the lectures now, it's non-zero. So A is invertible. Okay. So if A is invertible, then Cramer's rule applies. Okay, something to note here, you see? Something to note here. You see, xi is determinant of this weird matrix divided by determinant of A. If determinant of A is 0, what happened? The solution will not define. Okay, so it's another things to see here. Okay, so Cramer's rule apply. So uh what number you need to compute here? So x1 is equal to determinant of a1b over determinant of a, and x2 is equal to determinant of a2b over determinant of a. All right. Okay. So can anyone tell me what is the matrix A1B here? What's the matrix of A1B? So you replace the first column by the vectors B. Okay, so what do you get? Replace the first column of A by vectors B. So what do you get for the first column here? Huh? 11 and 12, which is the B vector. How about the second column? Minus 3 and 6. Okay, so you keep this and then replace this by the B vector. Okay, so this is the A1B. Determinant of A you already compute, which is 15. So what's the determinant of A1B in this case? 66 plus 36. Is it such a big number? So what do you get? 210, 15. Can you simplify this? I think you can. 3533934. Okay. How about A2B? Okay, A2B. Let's see anyone from this row can recognize what is A2B. Anyone from this row? This row here, the middle row. What is A2B? What's the first column? 2, 1, good. What's the second column? 11, 12, good. So you replace the second column with the B vector, and then you keep the first column. So determinant of A is 15. So determinant of this thing is what? 24 minus 11. Okay, so what's this? 13 over 15. Okay, both these numbers is weird. Okay. I saw that some of you in your exam very good. You do checking, okay? Because in my tutorial answer, I also do checking. So I hope you also can do checking on this. So do try and check this answer is correct or not. So you're gonna sub this AI S2, sub them back into the equation. Okay? Try and sub them back into the equation and then check whether you get 11 or 12. Okay? Try make a habit to do it. Okay. Should we do the next or not? You want to do the next or you want to do this or you want to try at home? Ah, do it. Okay, let's do it. Do it. Yeah, let's spend about 5 minutes. Try it out. I'll do it together and then we will check the answer. I think the number getting larger and larger. uh, how about let us see what to do, and then you can finish the computation, and then we'll check it out. Okay. I think it's not appropriate to do this large calculation here. Okay. So let's go through what we need to do before we go and compute this determinant thing. Okay. So first thing you need to check is whether the matrix in the matrix equation has non-zero determinant first, okay? Before you can use Cramer's rule. So so you got your A out, okay, from the coefficient matrix, okay? And then you can find the determinant any way you like to find. You can use cofactor expansion. You can use the elementary row reduce first, and then see how it changes under elementary matrix. Then you can get out. Did everyone get this number? Minus 132. Huh? Yeah, okay, good. So it's non-zero. Non-zero, that means it is invertible. Invertible, so you can use Cramer's rule. So how to use Cramer's rule? So in x1, so you replace the A with the first column vector of A with B first, and then compute the determinant, divide by the determinant of A, the original determinant, and then you will get the answer. X2, you will find the determinant of the matrix A, where the second column get replaced by B, and then divide by the determinant of A. S3, you replace the A with the third column in the A matrix with the B vector, and then compute the determinant, divide by determinant of A. Okay, and then try and finish this computation, and then check together the answer online. Okay. Okay. Since it is 9:50, how about we take a break and then we come back for the inverse. Okay. Let's come back at 10.你照相给我的那个是吗？你照给我。就是哦，我们不交。不交那个啊，我还没有看呢，其实。就这个。好像我有注意到课本有这个东西。就是简单一些，就是算的，就是是不是？就先是5对角线，这个叫4对角线，就是这3个数相乘，加上这3个数相乘，加上这3个数，然后这3个数，这3个数。哦，那如果 n by n 呢？只有3乘3，可以这么做。只有3乘3？对。4乘4啊不？那么4就要按照就是把它化成3乘3再这样。就是用那个方法。哦，这样的话就不对，这只有3乘3。不知道，这样就意思说要多学一个东西，就是说哦，空调，太冷了。没有，这样的话就多学一个东西，因为如果这个的话，就直接可以算 n 乘 n。这样除非这个方法可以4乘4也有，5乘5也有，6乘5。那个他说画起来好。画起来吗？有画的方法，但是应该是还不如那么。对，对，可以用。你可以放去那个上面，介绍给我。哎，你昨天你记得我有把我的那个插头带回家？哪个插头？这个插头啊？你昨天有注意到？没有。哦，嗯，哦
愚蠢的小女人，对，只听讲真风，
我是第6版的题目，这是第6版。
反正是从那个
这是练习题还是笔记？对不对？我是说我们的版本会不会用的不一样？用的是哪一个版本？6版的。版
就是这里，
没关系，
这是哪？
很厉害。这个不是 low reduce actually。
有没有？这个对，这个男子，那他是这，这个什么想法？对，这个感觉
哦，他只是说，嗯，因为它可以有些灵，有些不灵。
对，但是
对，
这个解释说的是，
没问题，这是我写的，
对
这我写的。
对，
嗯，
嗯
我看看。
嗯，这一点，嗯
嗯
嗯，
，every entry is 写什么东西？every is not just 有看一下，应该是要说，can be non-zero。OK，等下我看看，if it is 嗯嗯嗯，OK，不要写这个，我直接写一个 example。哦，一是个信托里面的我是朋友办的。应该是可能放东西。嗯
这是一个，对，然后这个，
嗯
图和图，
嗯
这几个我这个，
嗯嗯
别对你这
嗯
些，
嗯嗯
但这些图完图完它还有银行会什么这个地方都所有写后面，不能当图，当图也可以是有关那个当图，
呀，它有时候 on to，有时候不 on to。哎，给我想想，给我想想。OK，这个是 for 每一个啊，对，这个要 on to，对对对，要 on to。
那这个有完图案吗？
没有，它这个没有 solution 的，就我 OK，我记得我写这个东西，我这个东西我在写的时候是 for every b，是不是这个？昨天我记得我写这个，但是我记得我写的是 for every b，昨天吗？哪一天呀？昨天 HGR 昨天今天前天我写在哪里啊？你这个好像不太完整，我好像是有写 for every b，所以如果 for every b 的话，对，这个要 one two，然后这个也不完补完，它都没答案了。哎，every b 对，应该是 one two，因为没有答案，at most one，
之前那个谁，
对，
从两个 post，
你有看的，
看了这个他
对
他写的三个，
对
嗯，
对呀，对嘛，
他也是很多写的上，那这个好几个，他就只有一个是，
因为我可以喷残嘛，我可以有 free variable，它可以是残的，就是 n 大过 n，
好像是长的，
长就是 m 乘 n 大过 m
嗯
啊，
嗯，
那时候就有 free variable，对吗？那开始
我先讲一下影响，其实
，OK，hello，okay, let's come back. Let's come back. Okay, let's come back. Okay, so uh, we want to use Cramer's rule to find the formula of A inverse. So this is our job today. So our job today is use Cramer's rule to find the formula for A inverse. Cramer's rule leads. Inverse. Okay, so let's lay out this strategy here. So how are we gonna use Cramer's rule to find A inverse? Any idea? Any idea? You want to solve a bigger system here, right? Okay. So you can solve it by columns, right? Columns by columns. Okay. So if you multiply, okay, let me split it into B1, okay, X1. Okay, don't want X1. Okay, let's use B1. B1, B2, up to Bn, you will get the identity matrix, which is the standard basis. Okay, so can you split them into n matrix equation here? Right. So if you multiply A B1, you should get B1. Can everyone imagine this multiplication here? Yes. Okay. Is it okay? Can you imagine? Can you imagine or not? Hello from the back. Can everyone imagine this matrix equation here? Okay. 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 So really, we want to know how to solve each of these. We want to solve each of these. matrix equation. Okay, so to solve this matrix equation, we already know that from the Cramer's rule. What should we do? What can we do? So we can, by Cramer's rule, Cramer's rule, we can compute. How should I name it? Let's name it. B11, B12, B13, and so on. Okay. So the first subscript coming from which row you consider, and then second subscript consider label the sequence in your vectors. Now that B11 is equal to determinant of A, A, A what? A1, A1, yep, A1 EI, AE1 replaced by determinant of. Okay, and then B12 is determinant of A2 EI replaced by determinant of A, and then so on. Okay, so you can compute the whole row. Is everyone following? Everyone following? Following? Okay, so you can imagine that you can do this and then repeat for a different E2, EN, B2, and then so on. Okay. Okay. Okay, so in this case here, okay, so a so what about this? What about this? So let us see one of them. Okay, see one of them. What is determinant of AIE1? Okay, let's see what is this thing here. Okay, so what is E1 D1? So how should we do this? So let us make these things smaller. Mouse, new animal. Okay. Okay. So actually, what is determinant of A1 E1? Okay, let's look at one of them, and then we will deduce what is the rest. So what is A1 E1? So you have your E1, you have your A1. You replace your A1 with E1. Okay, the first column by E1, and then you have the same column from your A. So what's this? What's this? What's this? What's this? If you use cofactor expansion, what do you get? What would you get? Okay, if you cannot imagine, let us try something. So try something like this. Okay, let's restrict to 3 by 3 cases again. Restrict. And then call it A21, A22, A23, A31, A32, A33. Okay, so what happened here? What if you want to compute a determinant of this case here? What do you get? What method can you use? You can use cofactor expansion. Okay. In particular, which row or column you want to use? First column. Okay. What is first column? Is the standard basis because it's the one with the most zero. Okay, because you only need to do one calculation here, right? Because there's only 1 0 here. So you expand along here. Okay. So if you expand along here, what do you get? Is you have the 1 multiply with the minor that you get by removing the first row and the first column. Okay, so which is the original determinant of A11? Okay, you throw away the first row and the first column. Right, following? Okay. So what do you get? Actually, what you get is the 1 plus 1, the determinant of A11. Okay. So this thing is what? This thing is the core factor. Okay. So the determinant of AIEJ is actually the core factor. Okay. Okay. So that means what? Is the core factor divided by determinant of A build up your A inverse. Okay. Following. Okay. So hence what you will get is A inverse equal to 1 over determinant of A C11, C21. Okay, this is, I should name it as a C11 first. And we'll write it down. C11, C21, CN1, C12, dot C1N, C22, C2N. So, okay. So, the inverse of A is actually 1 over determinant because coming from the Cramer's rule. And then the core factor come out by computing the determinant of A, where the I column replaced by the EJ, which is the core factor. Any question here? Any question? Okay, so not that. Okay, so there's a warning here. So there's a warning here. So warning here. So not the order of Cij in the inverse of, okay. So let's name this big matrix here. So let's name this matrix here. Let's name it adjoint of A. Okay. Not that the order of Cij in the adjoint of A. Okay. Notice the order of Cij in the adjoint of A. Okay. Because usually when we write matrix, right, we will write A11, A12, A13, A14, usual matrix notation, and then A21, A31, and so on. Okay. So maybe ANN here. Okay. So you can see that this number here swap. Okay. It's like the transpose of this guy. Right. Everyone see it? Everyone see it? You see? Here is 1, 1, 2, 1. But 1, 1, 2, 1 should go downward in usual matrix. So this means that this arrangement is the transpose of this the original original notation for matrix. Okay. So when you compute, so when you compute the core factor, right, be careful how you place them. Okay. Yeah, be careful how you place them. Okay. Yeah, be careful. And yeah. Okay. So the reason why this is a transpose of this original matrix is due to this computation here. It's due to the computation here. Okay. If you try to compute A2, E1, and so on, when you change these two number here, then you will see that this matrix here will appear. Okay, but we won't do it here, but you can try it out. Okay. Okay, how about let's try use this formula here to find the inverse of this matrix. Okay. I hope it's not too difficult this time round. How about we do it together? Okay, let's do it together. Okay, let's do it together using the inverse. Find the inverse of the matrix. Okay, so before finding the inverse of the matrix, we should the same method, right? We need to check whether this matrix is invertible or not first. Okay, before we dive into computing it. So let's not use cofactor expansion to compute it. Let me show you another way to compute this matrix using the elementary matrices. Okay, so if we want to compute this matrix here, so my idea is I want to quickly reduce it to a triangular matrix first. Okay, so what I would do is I will do row reduction, row replacement. Okay, so for example, I would use R2 minus half of R1, and then R3 minus half of R2. Okay, because I know that if I apply this elementary matrices, the determinant doesn't change. If you interchange, the determinant will change by -1. If you scale one row, the determinant will differ by a scalar of differ by that scalar. Okay. So if I do these two row replacement, I don't change my determinant. So it is this determinant of this matrix is equal to the determinant of this row reduced matrix. So what do I get for second row? I get 0, and then -3/2. Please let me check if I'm correct or wrong. -3/2. So it's minus half. 0. 4 minus half, what do you get? 7/2. -2 minus 3/2, you get -7/2. Correct. No, no. -2 minus 3/2. Yeah, I think correct. Okay. So what's this? Okay, now I use cofactor expansion. So I miss out my method. Okay, I use cofactor expansion. So what do I get? I get 2 times the minor 3/2 minus 1/2, and then 7/2 minus 7. Okay, what do I get? I get 21/4 minus plus 7/2. Okay, 7/4. Okay, so I get 2 times 28/4, 2, 1, 2, 2, equal 14, which is non-zero. So A is invertible. Okay, so after A is invertible, then we can use the Cramer's method. Okay, so let me copy this. So let us recall what's the Cramer's method first. So A inverse is equal to the 1 over determinant of A. Okay, remember the factor coming from the Cramer's equation, and then the adjoint of A. So C11, C21, C31. Okay, in this case, because 3/3, C12, C22, C2, C32, C13, C23, C33. Okay, so what is C11? Okay, what is C11? Remember how to compute this cofactor here? So let us bring out the signature, the plus minus thing, plus minus plus, minus plus. Okay, so this signature will correspond to the power of this minus one. So the power of minus one is equal to the sum of the ij. So in this case, 1 plus 1. Multiply with a11, and then the determinant of a remove a11, the first row and the first column, the minor. Okay, so in this case is minus 1 to the power 2 times 2 times what is determinant of a11? What is a11 here? What's the minor here? So the minor here is removing the first row and the first column. And then what do you get? You get minus 1, 1, 4, minus 2. Okay? Up to here. Everyone okay? Following? Recall the cofactor and expand the formula from yesterday. So you get 1 times 2. See, this is 1. So I like this table a lot. You don't need to remember this. You just remember this. Just follow this sign here. Okay, 2 following from this a11. What is determinant of minus 1, 1, 4, 2? Is 2 minus 4. 2 minus 4 is minus 2. So the first entry is minus 4. Okay. Okay, let me do 2 more, and then we will work out the rest together on your own. Then we will check. So how about C21? Okay, what is C21? So C21, the sign is minus 1, and then 2 plus 1 times A21, determinant of A21. So equal to minus 1, okay, which matches up here. Wait, am I correct or not? Row 2, wait, row time column. Row 2, row 2, row first column. Yeah, correct. Okay. So determinant of A21 is what? Determinant of A21 is what? Sorry, yeah. So A21, the minor is 1, 1, and 1 minus 2. Because you have to get rid of row A. I think I'm wrong, right? Row 2, column 1. So it's this guy here. Okay. So this is, okay. Let me make it clear here. So this one is row. This is column. Because if you swap, right? If you swap it, then you will get the transpose of this guy, which is wrong usually. So first number here refer to row, and then second here refer to column. So it's the second row, first column. So it's this guy here. So this is 1, correct? This is minus, correct? And then A21 is 1, okay? So, but this one is wrong because we are removing second row and first column. So 1, 3, and 4. This one is a 1, 3, and 4. Okay. So just always remember that first is referring to row, second subscript is referring to column. So second row, first column. Okay. So what's this? This is minus, determinant of minus 2 minus 12 is equal to 14. Okay, let's compute one more. 3, 1. Okay, 3, 1. So what's 3, 1 here? So minus 1 to the power 3 plus 1, A31, determinant of A31. So minus 1 to the power 4 is 1. Okay. A31 is what? Is 1. Okay. Then the determinant of A31 is the third row, first column remove. So you get this. So you get minus 1, 3, minus 1, 1. Then what do you get? You get 1 plus 3, which is 4. Okay. So this is C31. Okay. What do you think? You want to finish this computation? Finish it? Okay, let's finish it. Okay, maybe about 5 minutes. Let's finish it. You finish on your own, I finish on my own, then we check. Okay, our goal is after we obtain this matrix, right? We try to take the product, see if we get identity or not. Okay, if we get identity, then we win. Okay. If anyone got it, we can check together. Anyone finish? Anyone finish or not? Or finish verifying? Finish? Anyone got this matrix or not? What matrix do you have? See? What matrix you get? Anyone got the same matrix or different matrix? Huh? Yeah, what matrix you get? Different. No, let me know your number. Never mind. You just tell me your number. Like this. Okay. How about the rest? You get this one? Okay, let me check some name and then I ask. Find some guy. Zhen Fang Hao, is it here? Okay. You ever finish? Okay, okay. Take your time. Wang Ye. I don't finish. Okay. Raymond. Okay. What matrix you get? Mhm. You also 7. Okay. And 6. Okay. So I think I have definitely wrong at C23. So C23 is what? C23. 23. I get the wrong minor. So it's a 2114. 2114. So it's a 8 minus 1. 2, 3. 2, 3. So it's this one, 1. Okay. This is a 7. Okay. This one, no issue. 2, 3 is 7. Eh? Minus coming from the sign. Good. This is a minus 7. So minus 7. Okay, so we have some disagreement at C22. So what's C22? So C22 is minus 1. The signature here is plus. So minus 1 stay. Determinant of 2 minus 2, 3, 1. So we get minus 4, minus 3 is 7. I think this one is correct. Raymond is correct, I think. Okay. Is everyone getting this? I think this is pretty close already. Should be this answer. Okay. Okay, some of you get this. So the next step is to multiply these two together. Okay. If you multiply these two together, do you get identity matrix or not? Bit nervous, huh? Not sure. We get the identity matrix. Usually when I do this test, most probably is wrong. So let's see. Hopefully it's correct. Okay, let's test A inverse A is identity or not. Okay. You want to get identity, this thing is divided by 14. So you should hope for 14 here, right? So is this 14? Minus 4 times 2 plus 14 plus 4. Why is it not 14? So there are two possibilities. So one possibility is the determinant is wrong. The second possibility is the cofactor is wrong, or the formula is wrong. Okay. So what is the possibility? So I have to go and check on. This is the usual life. Yeah. You make mistake on. There's not always conflict. Always right. So is my inverse determinant wrong or not? Or anyone can plug into determinant calculator straight away get it to check whether this is 14. This 14? So determinant of this matrix is what? Is it 14? Okay, I just plug it into a calculator and check. Determinant of a 3x3 matrix. Okay, let's check. Let me ask my computer. Anyone verify this? You also can let me know. Have you verified it? Is this correct or not? 1, 4, -2. I hope it's correct. Yeah, it's 14. 14 is correct. So something wrong with this. Huh? C33 what? C33 is wrong. Okay, never mind. C3 is wrong. Yeah. Huh? Ah. Ah. Okay. Wait. Let us go back. So we are wrong at the formula of cofactor, is it? Okay, let's go back. What's the cofactor formula? Here we mentioned about it, right? So this is the one. Okay, let me go to chapter 3. So cofactor. Oh, cofactor is without the AII one. Yeah. Okay, good. Okay, good point. Okay, good point. So yeah, okay, very good. So you see, so the AI one will contribute to compute the determinant of A, but with I forget. Okay, I forget that actually we only define cofactor without the AI. Okay, without the coefficient. Okay, so we have an extra AI here. Okay, so it's not the whole thing. It's not the whole thing as the cofactor, but just the -1 signature and this determinant of the minor. Okay, so let us learn a lesson here. So cofactor is just the I call it signature, that part. Okay, the signature plus or minus signature with determinant of minor. Okay. Okay. So let's try again. So let's take all the factor away. So remember the cofactor is the signature with the determinant of minor. Okay, let's all learn this lesson in particular for me. Okay, so let's take away all the extra factor away. Let's see what we have this round. So if we take away 2 here, so let us use the red pen. So if you take away a 2, we get -2 in this case. And then if we take away 1, we still get 14. Take away 1, get 4. Take away 1, get 3. Wait, sorry. This one, C1, 2 is 1 row. So second column. Okay, this one correct. So we have to be careful. So we just need to be careful on this guy here. Okay, so these 3. So this 3 is what? Is C11. And then this is C what? C13. This is C22, and then this is C23, and then this is C33. Okay, we need to change this. So C13 become 5, okay, and then C22 become -7, and then C23 become, hey wait, this is C2, oh sorry, this is C32, sorry, C32. So C32 become 1, and then C33 become -3. Okay, so let us change this coefficient here. So we change this guy. So the first C11 become -2, C13 become 5, C22 become -3, C32 become 1, C -2 become -3. Okay, is that right? That matches up? Okay, all good. So let's move this again. So we should hope that we can get it this round. So this is the usual life process. Let's try this again. Move it up, move this up, and then make it color. Okay, let's try again. Start again. So we want 14 in the first entry. -2 times 2 plus 14 plus 5. What's this? 15, no? Is it? 15. I want 14. Anything wrong again? It's not 15. It's not 14. Hey, did everyone calculate this again? Everyone check this answer. Is this correct or not? Is this correct? No. C31. 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 Oh, wait, what's going on here? C31 is 4. Oh, I changed the wrong number, is it? I know. You see, this is the problem. So this is the transpose of this guy. So, okay. Can you tell me the whole matrix? So C11 is -2. C21 is 14, right? C31 is 4. C12 is 3. C22 is -7. C32 is 1. C13 is 5. C23 is -7. C33 is -3. Okay, let's try again. Third attempt. Third attempt. Okay, let's put it back. So now this one happy already. This one become 4. Okay, good. So I want to hope for the next two is 0. So -2 times 1 plus 14 plus 4 times 4. Is it? Let me check. 16 minus 2, 14, 14 minus 14, 0. Good. Okay. -2 times 3 plus 14 plus 4 times -2. So what do you get? 6 minus 6 minus 6 minus 8 minus 14, 14 plus 14, 0. Okay, good. This one also good. The next one, 3 times 2 minus 3 times 1, 7 times 1 plus 1. So 6 plus 1, 7, 7 minus 7, 0. Okay, this one also good. 3 times 1 minus 7 times -1 plus 1 times 4. What do I get? 4 plus 3, 7. 7, 7 plus 7, 14. 14 divided by 14, 1. Okay, this one good. So 3 times 3 minus 7 times 1 minus 2 times 1. What do I get? 9. 9 minus 2 is 7. 7 minus 7 is 0. Okay. Okay. 5 times 2 minus 7 times 1 minus 3 times 1. So 10. 10 minus 7 minus 3. 0. Next, 5 times 1 minus 7 times minus 1 minus 3 times 4. So 5 minus 5 plus 7, 12, 12 minus 12, 0. Okay, good. 5 times 3, minus 3 times 1, minus 3 times minus 2. So 15, 15 minus 7, I get 8. Wait, wait. See. Let me see. 15 minus 7 plus 6. How was this? Am I wrong? Am I wrong or not? 5 minus 7, 15 minus 7 plus 6, 21. Ah, correct? Right. 21 minus 7, right? Ah, right. Because 8 plus 6 equal to 14. Okay. So, yeah. So what we'll get is 1 over 14 times 14, 14 on the diagonal, and then 0 on the other. Okay. Then we will get 1, 1, 1, 0, 0. Okay. Everyone follow? Is everyone following? Everyone following or not? Okay. Yeah. So you can check that this guy go to 0. Okay. When the terms go to 0, you can see that how these numbers split, how they cancel out each other differently. Okay. Okay. All right. So the lesson learned today is cofactor is a signature with the determinant of the minor. Last time when I tried to do the tutorial question, I accidentally transposed it. So I transpose this cofactor, this adjoint. Then I also cannot get the inverse. Then I found out it's the transpose of it. Yeah. Okay. Okay. So I'll learn from mistake. Any question? Any question about this? Any question from the back? Then from the right. Okay. From the left. No. Okay. So yeah. So basically this is all for this chapter. For this chapter, this is all. Should we go to the next chapter or not? I think we have a whole week for chapter 4, but what's the time now? Maybe let's talk a bit about vector space first before we go into quizzes. So how many minutes we need to discuss quiz? Let's spend 20 minutes. Okay, let's talk about vector space. Okay, how about take a rest first? We come back at 11. And then we discuss about vector space for half an hour and then 20 minutes for quiz. In the meantime, you can come and collect your quiz for yourself. Yeah, you can collect one by one. Don't be too crowded here. Too crowded. 什么有什么用？这么复杂？这个哈。 不能啊！如果你是 n by n 的话，
那不算死
我感觉这个的方法就很，就是
算到黑地就算出来。
对啊，
没有这个你 matrix 越大，它应该是越
很无效，它不如用那个
哪个
a 乘 a 的
inverse 也
inverse
叫他们去解那个方程，
等于 i，那个多好算，就做一个那个
一样的哦，一样的哦。这个东西跟这个跟那
这个太难算，那个做一个初等航变就是那个，
那个
就把它们合在一起，然后就可以。
忘记给他们签什么
我都等那个。
？OK，等
这个我真的不觉得有什么用，考试不会让我强制用这种方法。
可能会耶，
不要，千万不要这么出题，
不然学来干嘛？
对，这不知道学了干嘛？这么
太复杂了。就像1+1等于几，然后把1+1把那个1变成2减1的。
可是如果5乘5的，5乘5的你怎么解
？5乘5的
啊，
我之前的那个不是就是这个东西右边附一个癌矩阵，然后用乘法左边画那个画出来。
哦，
他用这个5乘5，他不是要求4乘4的那个什么 defect， 然后那不要求9个不25个4乘4的那个，怎么算死啊？
要想下来嘛。但是你如果去 row reduce 哦，你 row reduce 5个东西哈，但是你 row reduce 五个 matrix equation 也是要 row reduce 啊。
我是有解释，当初你的无限个解，但是这个没有无限，
不一定要无限结的，不一定。
但是你就跟我讲
啊，
你 solution
哪一个 solution？
它是那个有限的，就是 unknown，那怎么consistent 的，然后 consistent 的，后面是对应的，那个是 unknown 乱出来那个 unknown。
哦，可是那个不是一对应。
所以说这个就是
早上他问了，那个东西不是一对应吗？
对，
不是一对应。就是如果你有这个，你是有这个，但是不是一对应。
我这么想不行，我就要扣2分。
有看看。因为你想象一下，如果有这个的话，这个也是on to 啊。如果把后面2个丢掉，哇，搞什么意思？
是 on to。对啊，虽然肯定是，
但是它不是
不仅 on to 还是1对1。
对，但是这个情况它不是 infinitely many solution。
确实哦，
是吗？
那怎么解释？
怎么解释？就是说，
那怎么说它是 on to？
不是，你解释是说它不 on to 嘛，对不对？它不 on to 的话，就是它可能 inconsistent 的。
可能 inconsistent。
对。对，
什么？这个怎么解释
？The system can be inconsistent。
我事情看比，就是它可能有解，可能没有解。
对，有些 B 它有解，有些 B 它没解。
我就这儿扣2。
所以你现在这个的那个排法，你是用这个，就是1、2、1、3，对，不是用这个，就本来就这样子的，然后它真正是这样子，
没有真正是这样子，
真正是这样子，
怎么解释？
对，这是法律啊，是这个还是这个？我有点忘了，就是减24，因为我不懂这个值是怎样算的。
哦，这个数字是从这个数字来的。刚才我们算的只是说我们多了那个 aij 的东西，对，
就举反例。
aij 是3乘3，
不是，我们刚才我们一开始算的这个嘛，我们多乘了这个东西进去。
所以前面的不用
不用那个 aij，就是
只是那个 determine 而已。
不用这个部分。我们我们把这整个当做 cofactor 嘛，其实不是，
这么不用的。
为什么不用？
就这么那个 inverse 这个对，
它算出来刚好就是不用，
对啊，
它就是不用，它算出来是不用，就是我们在 刚才我们在讨论这个 formula 的时候，就是不用的。我们在讨论那个这个的时候，就是不用，这个，你看我们在算这个时候，那个 AI 没有跑进来，你看是1乘那个 minor， 里头没有 minor， 那个 AI 直接是没有进来，你看，它就是那个
我考试要一定要写这样子减一，然后1加1这样子，还是我可以直接一个减，然后你们就
我接受加减罢了，加减对就可以了，因为我自己也是这样，所以我教你们去看那个加减的那个 matrix。
对，我们是用这个，就我们
啊
2 1对，是这样子。
那个21啊，对，21是这个呢，这个
然后减2减12，然后是4是32
啊，
然后就
可以，
然后14，然后就放这样啊，懂了。
行，你这错2分是因为没有写 traverse，不是那个。
你没有解决 onto 的问题。
写这个要写 B 是吗？
是啊，问题是你没有说它 onto 不 onto 啊，你都没有写。对啊，你都没有。呀，
下课的时候问，因为我觉得它是 onto 推证了有一点问题，因为
每一个对，
所以说他如果是这个情况的话，
你看这个情况，你看 every row has a pivot， 你这个没有 every row。
对呀。
哦，但是你这个不 onto 哦，这个你看221它就 inconsistent 不 onto。
不，它的 x3不是 free 吗？那它就是 onto。
没有啊？
没有吗
？onto 的意思是什么？每个 b 都要有一个解。
对。
221有没有解
？221有没有解？221是什么东西啊？
如果我把这个 b vector 变成221的话，221没有解，对啊，没有解啊。onto 要每一个 b 都要有一个解啊。
对，但是它对，
每一个 b 啊，一个不够，一个不够。OK。Someone didn't come. Eh ya, tu Chang Xiaoyi not here. Your friend, Chang Xiaoyi. Why not here? Why? Chang Xiaoyi, you know her? Not here. Here or not? Not here. Eh? Okay, I will pass the attendance down. Okay, you get the your quiz. You can take a photo and make a record because you need to return to me because the school need it later. So after class, you have to return your quiz paper to me, and now you can take a photo of it. Okay. Before you leave, you have to pass it back to me. Okay, do you want to discuss quiz first or you want to do vector space? Do vector space first, huh? Okay. After discussing quiz, I think you don't have food already. Okay. Okay, vector space. Let's start chapter 4. So already finished chapter 1, 2, 3. Okay, let's go into chapter 4. So vector space. So what's a vector space to you? What do you think of vector space when you first see it? Okay, what's a vector space to you? Okay, maybe you think there's an arrow Okay, always you will think vector as an arrow, right? As an arrow, okay? So there's a direction, you have a direction. You also can compute a magnitude if you have learned in high school before. And you can draw an arrow, okay? So basically, this is the vector space we have seen in our early stage. So really, vector space, what's vector space? It's a set of objects, okay? We call it vectors. And there are two operations on it, okay? We have seen this before already. We define the two operations on the vectors in Rn, which is vector addition and scalar multiplication, okay? These two, okay? We still have these two. So we try to generalize the idea to any set of objects that satisfy similar properties, okay? Two operations in this set, we want addition and multiplication by scalar, and then subject to 10 axiom here, okay? As long as you give me a set of objects, I can add them together, I can multiply by a scalar, and satisfy these 10 axiom here, then this space, this set, we will call it a vector space, okay? Let's see what this 10 axiom doing. First of all, you want that if I add two elements together, it is still the element in the set. Okay, so this is what we call closed under vector addition. Okay, we have encountered this idea before. Secondly, we want the addition to be commutative. So u plus v is equal to v plus u. And associative. So I need to know how to add three elements together. How to add two elements together is the same as the order doesn't matter. If I want to add three elements together, and then equal to, I add the last two first. Fourth, I need to have a zero vector inside my space, which is the identity, which is the additive identity. So everything add to this zero, I get back myself. Okay, get back the original vector. Second is, can I add to any vector and then I return to zero? This is called the additive inverse. Okay. Okay, I want this to be true as well. I can add to a identity, I get back myself. I can add to a negative of me, then I get zero. Okay, it's like if you know a bit of physics, it's like a matter and antimatter. So when matter and antimatter mix, it become nothing. Yeah, in fact, this vector space is inspired from physics. Okay, for any C in R, in any vector, I multiply them, is still in my set. So this is closed under scalar multiplication. It's closed under scalar multiplication. So you can see that the first 5 part is about vector addition on the first operation. And then the last 5 part is about scalar multiplication. Okay, so how scalar interact with vector addition? Okay, so 7, what we have, how scalar multiplication interact with vector addition, we can bring the scalar into it. So this is called the distributivity. Okay. Similarly, if you have C plus D, 2 addition, so you can see that what's the difference between 7 and 8? 7 inside the bracket, it is vector addition. 8 inside the bracket is scalar addition. Okay. So both of them are distributivity. Okay. And then 9 is a bit similar to associativity. Okay. So if I want to multiply, for example, 2 times 3 times V, is equal to, I can multiply 2 times 3 first, and then multiply by 3. So I get 6b. And then 1 times u is u. Okay, so it's the identity. So it's the identity, scalar identity. Okay. Scalar identity. Okay. Note that I hide something here. I didn't tell you what is scalar actually. So scalar here actually need to be a specific things, specific number system. Okay. For now, you can take the scalar. Usually in this course we have in Rn. Okay. Sorry, in R. So you take real numbers. So real numbers are all the rational and irrational numbers. Okay. Rational and irrational numbers. So for example, we already see for the past 3 topics, we see that Rn is a vector space. Okay. So if you take any vectors from this, so you have Rn because you have vector addition and scalar multiplication. Remember? So if you take vectors here, you can add 2 vectors together. Okay, this is what we defined before. And then we know how to multiply scalar to vector, which is defined to be multiply on every entries. Right? Remember? And then how you add the vectors, you just add entries by entries. Right? Okay. Just recall what we did. Okay, so Rn is a vector space. And then you can check that all these satisfy as well. Because Rn is just n copies of R. Okay, R satisfy this condition here. So what is the other examples? So one of the example is the set of infinite sequences. Okay. So if we want to say the set of infinite sequences is a vector space, what 2 operations do we need? What 2 operations do we need? Remember, what is the 2 operations we need for vector space to hold? We need addition and scalar multiplication. Okay. So if I say that this is a vector space, so you need to tell me how to add 2 infinite sequences together. Okay. You tell me, what do you think? How should I add 2 infinite sequences together? Huh? How to add? What do you think? How to add and how to multiply? Use A. So you need to tell me how you define these 2 things. How do you add 2 infinite sequences? What do you think? Any idea? Any idea? To add? Any idea how to add 2 infinite sequences? Any idea how to define this? Just guess, just guess. Be creative, huh? Just like vector. So you want to add entries by entries. Okay. So you add the first entry to the first entry, the second entry to the second entry, and then so on. Okay. How about multiply by scalar? Do you do? Also like vectors. Okay. A, C0, multiply A to everything. E2. Okay. In fact, you can see that this infinite sequence is like an infinite dimensional R. Okay, it's like R infinity. Okay, because you cannot list all of them, so you dot 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 dot. Okay. So what's the zero vector here in this case? What's the zero? What is the thing that add to a vector, you get the vector itself, or the sequence itself? What's the zero vector here? Huh? All zero, okay? So the zero vector here should look like 0 at every spot. Okay, so that by this definition here, when you add to any sequence, you get back yourself. Make sense? Make sense? Okay. So what else do you need? And then you need for each v, you need a minus u such that u minus u is equal to 0. So give you a sequence. What's the minus of this sequence that you get 0 vector? What's the minus u in this case? Okay, let's say u is C0, C1, C2, dot, dot, dot. What is minus u? The sequence that you add to u such that you get the 0 vector. What's the sequence? Yes. What's the sequence that you add to C0, C1, C2 such that you get the 0 vector? Using the addition you define here. Idea? What's the thing you add to the sequence such that you get 0 vector? Huh? Minus c. So you just take minus at every spot. Right? And we can verify this. So u plus minus u is what? Let's see, is this how it written? Yes, that's right. So u plus minus u is what? Is C0, C1, C2, dot, 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 plus minus C0, minus C1, minus C2, plus dot, dot, dot. Okay, so how we define the addition? We just add component by component, which is C0 minus C0 plus minus C0, and then C1 plus minus C1, and then so on. Okay, so what's this? So this is actually 0, 0, 0, and so on, because R is a vector space such that minus C0 is the thing that when you add to C0, you get 0. Okay, so this is the formality of the in this vector space. Okay, so really here we don't interpret as C0 minus C0. Okay, really, what is minus C0? Minus C0 is the thing that you add to C0, you get 0. Okay, because R is a vector space. Okay, yeah. Okay, so we don't interpret we don't interpret C0 plus minus C0 as C0 minus C0. Okay, so this is the formality of the mathematics. Okay, okay. So in this case here, 1 and minus 1. Okay, what is minus 1? Minus 1 is the thing that you add to 1, you get 0. Okay. This is fine. So what is 2 and minus 2? What is minus 2? Minus 2 is the thing that you add to 2, you get 0. Okay. Right. Okay. So negative of a number is the thing that when you add to the original number, you get 0. Okay, this is how we understand about the negative numbers. Okay. Okay, all right. What else we need to determine here? Okay, so we should already found, what did we do? So we already found this, we found the zero vector, we found the minus u. Okay, because there is, we need to find it. Okay, and then for the rest, you can verify yourself, because it's just the same as verifying the numbers, satisfying this condition. Just that there's more terms popping up. You understand? Okay. And why numbers satisfy? You can take it as a black box. This is how we define real numbers. Okay. When we reduce to real numbers, you can assume that all of these are true. Okay. When you reduce to the numbers. Okay. Okay. Next. Okay, how about let us start in a new page. So the set of polynomial of degree at most n. So let us spell out what does this mean. Okay, maybe most of you don't know what this means. So Pn, put down one of output. Okay, set of polynomial of degree of most. Okay, I swear you see polynomial before, just that maybe you haven't seen it by organize it in this way here. So this is defined as a set of polynomials. So we have a0 plus a1x plus a2x squared plus dot 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 plus an x to the power n, because at most n. So degree of the polynomials refer to the degree of x, okay, such that a0, the scalar, is in the scalars, or scalars, okay, scalars in R. So anything here. So for example, what do you have? Example inside an example. So example, you have 1 is in Pn, you have 0 in Pn, you have 1 plus x in Pn, okay? And then you have 1 plus xn in Pn, okay? Any combination, any linear combination of 1 x squared up to xn is in Pn, okay? Set of all linear combination of 1 x squared up to Sn, okay? So far, okay? So far, okay? Okay, so in this case, how do you add two polynomials together? How do you add two polynomials together? So given two polynomials, P and Q, okay? Maybe I write it as A0 in one polynomial up to AN xn, and B0 plus B1x, and then so on up to Bn. How to add two polynomials together? How to add? How to add two polynomials together? Add two polynomials together. Simple, you get something to say. Just like. Okay. Yeah, so you add the coefficient of the same degree, right? Okay, so if they have the same, the coefficient is coming from the same degree, you just add them. So like a0 plus b0 plus a1 plus b1 times x plus A2 plus B2 plus dot 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 plus AN. Okay, so is this like feels familiar to you or not? It's like how you factorize things, right? Okay, why you can factorize? Because you are living in the vector space. Yeah. So next time you see your high school teacher, you say, why can you do this? Because this is a vector space. Okay. 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 Anyway. So yeah. So what do I want to say? Okay. Next, how about applying? How about C times P? How about scalar multiplied any polynomial? What do you how you define it? You define it. Distribute. Yeah, distribute. So you just multiply on every terms. Multiply by every term. Every terms. Okay. Okay. So you might wonder, you see, the example here, you see the polynomial is so short. Why this polynomial so long? Right. So can I apply this long polynomial to the short polynomial? Did anyone have this question or not? Why this is so long and this is so short? The element here, isn't it short? Why so long? Right? So the idea here is this is the general case. Okay. So every polynomial can write as this length. Okay. For example, 1 plus x is equal to 0 plus 1 times x plus 0 times x squared plus dot 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 until 0 times x to the power n. Okay. Yeah. Okay. So this is the formality we're having. Okay. Okay. 1, 1, 2, 3. We still have 3, 7 minutes. Okay. So how about what's the zero vector here? What's the zero vector here? So zero vectors, remind you again, is the thing that when you add to the vector, you get back your answer. So what's the zero vector that add to every polynomial, you get back the polynomial? What's the polynomial that you add to every polynomial, get back yourself? Get back the original polynomial. What's the zero vector here? What's the thing that you add to A0, you get back A0. When you add to B0, B1, you add to A1. When you add to A2, you get back A2. What polynomial? Huh? The zero polynomial. Okay, so it's the zero polynomial. So the zero polynomial is when, it's the zero polynomial. It's zero. The zero polynomial. Okay, zero polynomial. How to realize zero polynomial in this set? How to realize zero polynomial? Why zero is in why? Okay, why this is true? Okay, why this is true? Why zero is in the set? Why zero polynomial is in the set? Why zero polynomial is in the set? What's the definition of the set? You can pick any scalar you want, right? So how you make the zero point? Huh? What? 未知. Enough? Just A0 equals 0? Every scalar. Okay. Okay. You take every scalar equals 0. Okay. Every scalar equal to 0. Okay, good. How about minus P? Okay. If you have P, what is minus P? What is the polynomial that you add to the polynomial itself, then you get the zero polynomial? What's minus P? If your P is this general polynomial here, what is minus P? What's minus P? Is minus P is the polynomial that when you add to P, okay, when you add to P, you get zero polynomial. Okay. So what's the number you add to A0? You get 0. What's the number you add to A1? You get 0. What is minus or minus a polynomial? B. What should it be? Negative. Okay. Negative of a polynomial. We haven't defined it, so you need to say more. We only describe the polynomial in terms of scalar. So you need to describe the polynomial in terms of scalar only. So what's the scalar should be? What's the scalar? -1. Negative 1 like this, -1. Then P, what do you mean? The whole line? Okay, just tell me what happens to each each coefficient here. Multiply by -1. Not multiply by -1. So okay. Yeah, still haven't get that idea yet. So minus P should be minus A0 plus minus A1 x plus minus A2 x2 to minus AN xn. Okay, why? Because when we do the addition, P plus minus P, okay, how do we perform this addition? Is using this here, okay, is you add out the corresponding coefficient, right? Okay, so the first one is A0 plus minus A0, okay, and then second you will get A1 plus minus A1 x plus dot 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 plus AN plus minus AN. Okay, up to here is enough. Okay, so just now I give a warning. We don't know. Okay, let me write this warning big. Let me big. We don't know A0 minus A0 is 0. We only know A0 plus minus A0 is 0. Okay, I know that high school we always learn that 1 minus 1 is 0. Okay, but actually in this formality we only know that 1 plus minus 1 is 0. So minus 1 is the thing. I can replace minus 1 with anything. I can replace it as an apple. So 1 plus this apple is 0. Okay, we only know how to add. We don't know how to subtract. Okay, so in this world we only know how to add, how to do scalar multiplication. We don't know how to do subtraction. Okay, understand? Okay, yeah. So this is the thing I want you to appreciate. Okay, maybe let's stop here and then we will continue again. And now we go into quiz. Any question about vector space? Quick question. Otherwise, we leave to the next lecture. We will continue this vector space again. Okay. Quiz. Let me bring something in. Okay. So as I said in the start of the lecture, so the average of this quiz is 19.4. I think considered quite high. And more than half of you is about 20 and above. So I think this cohort is quite strong. So if you think you are weak, I think you need to catch up. Otherwise, I won't think there's much scaling can do in this course. Okay. So I also understand that some of you are new to the course. So if you have problem, please come and find me. And then I have office hour tomorrow. Tomorrow at 8:30 to 12:30. Last week, I think there's only one come. Only one of you come. Yeah. Come to us. Yeah. So yeah. So try to make full use of my time. Not my free time, my office hour time. Okay. Make full use of my office hour time. Okay. Uh, okay, let me bring out the quiz. Where is it? Let me see. Check. Let me bring up the quiz. Not sync between my phone. Let me send using AirDrop. Okay. Okay, I have a solution from one of you, 罗英杰. I got this solution here. Let's share this solution. Okay, I like this solution because it's kind of nice. Looks like an art. This course is an art course, right? Yeah, it looks like an art. So I share this solution here. Okay, he scored full marks. Okay, let's see. So first question. So you are given a matrix equation here. Okay. I saw some of you still use primitive method to solve it. Primitive method meaning you use the variable substitution. Okay. It's not that you can't use it, but I wish you can learn how to use augmented matrix. Okay. Please do the tutorial question. Tutorial question will be very extremely helpful for you. Okay. So please learn how to use augmented matrix. So augmented matrix, after you set out the augmented matrix, okay. So it's okay if you not put a line or don't put a line. So my practice is to put a line in the middle, up to you. And then you will solve it until you get raw reduced echelon form. Okay. And then from the raw reduced echelon form, you get your solution. Okay, some of you, you don't get to raw reduced echelon form. You get to you get to echelon form. Okay, you just get to something triangle. And then you use the primitive method again. So you kind of mix two methods together. Okay, so up to you. Okay, but if you can try do this, try this raw reduced echelon form. Okay, and then the nice thing about this solution is you do the check. Make sure that you find the right answer. Okay, so when you substitute back your solution, you get back 264. Okay. So who else? I think I saw Duan Tianci. Hey, where is Duan Tianci? Is it here? Duan Tianci. It doesn't want to admit, huh? I think you are here, right? It's not here, 端田. Who is 端田次? Huh? Who is 端田次? Not here? Not here? But the question is not here. So where is 端田次? Hello? Who know him or she? Who is the person? Anyone know? No, don't know. No, I just want to say you are very good. You do the checking. 端田次. And then one of you is Talia. Where is Talia? Oh, Talia is here. Okay. Hey, 端田次is not here, but the quiz is not here as well. Someone is taking the quiz. Or friends is taking. Not here. I haven't seen this guy before, you know, because this guy emailed me. So I think it's an AI. It's not here, but this person emailed me. But I see the handwriting. I didn't see the machine. Who is? Okay. Slowly I will find out who are you. Okay. Okay, you guys help me to find who is this person here. Contents. Okay. Okay. Any question on question 1? Should be good. Only handful of you maybe do wrong calculation, and then yeah, wrong calculation. So make sure be careful with your calculation. Okay, next for what values of A does the system have non-trivial solution? Okay. So you ask about solution again on a linear system. So it's equivalent to solve the augmented matrix again. So when you solve the augmented matrix, you will see that there's a variable floating around. This A here, it's floating around. So you see that there's some freedom here. Okay. If you set A to -1, you'll see that you will get a row of 0. Okay. Once you get a row of 0, you have a free variable. And if you have a free variable, then that's when you have a non-trivial solution. To this, notice that the B vectors here are all 0. This is a homogeneous system. Okay, so you're finding the null space. Okay, so the null space here. Okay. I think this one quite good. Everyone, most of you got it. Almost all. Okay, second page. Okay, in this second page, right? I'm not sure some of you squeeze your answer at the bottom here. I purposely move this question here so that you can write all your solution here. But you squeeze all your solution here, some of you. But anyway. So, okay, question 3. Determine the basic variables and free variables of the following linear system. So you have a linear system again. So it is also equivalent to a augmented matrix. So here, do you really need to row reduce everything? Or not? No. Because what you care about basic variables and free variable is whether they are the pivot variable or not. They are coming from the pivot or not. Okay. As long as you reach the echelon form, is enough. So in this case, you can see that this is the okay. So this is a raw reduced echelon form. So you can just stop at this step here. So this is the echelon form. Reduce echelon form. Echelon form. Okay. Wait. Yeah. Okay, yeah, right. So this one. This one. Echelon form. Okay. So from here you can already read out these two are the pivot. Okay. Some of you, I'm not sure why, you go and make this -8 into 0. And so your pivot change. I'm not sure how you do it, but it's not possible because, yeah, it's not possible. Yeah, it's not inside the rule, not inside the game rule. Okay. So you can see that S1, S2 are basic because of the pivot position here. Okay, and then if it is not the pivot position, then it is the free variable. Okay, yeah, that's all for this question. So this question only 3 marks. One for row reducing, one for basic, one for free. Any question for this? No? Okay. You can see that this set of questions, I think, allocate quite a lot of mark in towards the raw reducing step. Okay, so this course shouldn't be very hard. So it's quite basic. So basic tools, basic skill you need to learn is raw reducing. Okay, next, I think it's the hardest among the all. So assume that T is a linear transformation from R2 to R4. Okay. Such that when you add on the first basis, standard basis, E1, you get 3, 1, 3, 1, and then second standard basis, you will get -5, 2, 0, 0. Okay. So what's the standard base matrix of T? So how do you do? So you just collect this vector as your column vectors. Okay. So I think some of you very good. You write out everything such that you say that A is a matrix. Okay, it's a 4x2 matrix because it's going from R2 to R4. So it's a 4x2 matrix such that this thing here, E, F, G, H, such that this matrix here multiply 1, 0, 0 equals to A, B, C, D, where A, B, C, D, we want it to be equal to 3, 1, 3, 1, so that you will know that exactly what the first column is. Okay. You can write it out, or you also can just do it like this, like what Yingjie does. Okay. Second part is determine if the linear transformation is 1-to-1 or onto. Okay. There are a few ways to answer this question. There are 2 ways to answer this question. One way is to see from the raw reduction step. The other way is straight away see it from concept. Okay, so let's discuss the first way first, the usual way, the normal way. So the normal way you will do it is you raw reduce. Okay, so the standard usual way, not standard, but if you learn this course, so you reduce this system of linear equation, and the other is homogeneous. Really, these two are the same. You can do it. You can do this and then sub B, let B equal to 0, then you will get this. So you don't need to do twice. Okay. How to see answer from these two? Okay. Let me tell you this. So really, you just need to do 1 and then sub B equal to 0. Okay. Okay. And then what you do is you get your augmented matrix. So you get your augmented matrix. Okay. And then if you found that not every row have a pivot, then what does that mean? This means that you have a row of zeros. Okay, so that what? So that the system could be inconsistent for some B. Okay, so meaning you cannot find solution for some B. If you cannot find solution for all B, then it is not onto. Okay, so not onto. Okay, so in this case, it's not onto because you can see from this reduced form here. Not every row have a pivot. Okay. Yeah. Okay. If you found every row has a pivot, that means it is onto. This is the theorem. Okay. If every row have a pivot, then you have a. So let me draw it down. Every row has a pivot if and only if A is cannot say A is onto. A is a matrix, so it's the if the every row how should I say it? Every row of A has a pivot if and only if the linear transformation T associated A is onto. Okay, this is the theorem. This is the theorem. Recall theorem. Okay, recall theorem. Okay. Okay, next. So in this case, if you row reduce it, you can find that you can only find at most 2 pivot here. So you have a row of 0, and then you can make it inconsistent, okay, by picking different B. How about AS equals 0, the homogeneous one? So you can check that if every column, okay, so onto you check row, 1 to 1 you check column. If every column has pivot, then what? Then T is 1 to 1. Because the columns are linearly independent, so the only solution to the homogeneous system is 0. Okay. Or you can see from this augmented matrix here. So can you read out what's the solution? X1 is equal to 0 and X2 is equal to 0. Okay. So there's only a trivial solution here. Any question for this part using row reduction? Any question? Okay, the other part is using concept part. So how to use concept? So you want to show that it is not onto, right? Okay. Not every row has a pivot. You see, you have a 4x2 matrix here. Okay. If you have a 4x2 matrix here, at most how many pivot you can get? At most is 2. You cannot fill every row with pivot. Okay. So how to see from geometry? Yesterday I drew a picture, right? How you fit R2 into R3? I think only one of you wrote something similar on this line. So you cannot fill a large space with a small space. Okay. Like yesterday I said, you cannot use a plane to fill out the box. I mean, using just one plane. You cannot use one plane to fill out the box. Okay. So how this demonstrate using matrix? You can see that you cannot have pivot at all rows. Okay. There's no space for you. Okay. How about onto? So onto you can straight away find 2 solutions. Onto the sorry, 1 to 1. So 1 to 1, there's another thing. So if it's 1 to 1, if and only if AX equals 0, for what's the theorem? How to state the theorem? AX equals 0 only for S equals 0. Okay. What you can do is you find another vector that get mapped to 0. Can you easily find one? I think you can, right? Did you find one? What you can do is you can use this, you can try this. This one is equal to 0, 0. Let me see. Okay, it's just 2 coordinate, right? So can you find one? Is it easy to find? Hmm. 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 Is it easy to find? Hey, this is 1 to 1, right? So you cannot find. So you need to solve for s equals 0. So what's the concept you guys? Let me see. Did I record down? Oh, never mind. No have. Okay. Onto you can use onto you can use onto you can use. Oh, okay. There's one way you can see it. So we have the rank theorem here. So we have rank theorem which we learned yesterday. So the rank A plus the dimension of now A is n. Okay. So what's the n here? N here is what? M times n. So n is 2. Okay. And then from the row reduced echelon form, you can see that rank A is 2 as well. So the dimension of now A is 0. But this one is just from yesterday, so never mind. Okay. Dimension of now A is 0. So the only solution to the homogeneous equation is just 0 factor. Okay. For future, you can use this. Okay. But anyway, yeah, I see it. So 睿智 also use the concept where I think 张志堂, who is 张志堂 again? 张子堂or 张, okay, yeah. And then 段天赐 again. Seriously, this guy is not here. The quiz paper is not back here, you know. 段天赐 not here. You don't want to admit. Okay, there's one misconception here that I want to raise up. There's one misconception. Okay, some of you trying to prove inconsistent system. Okay, so what you do is you reduce to this matrix here. Okay, and then you say that this is not onto. Okay, because 2 is not equal to 0, 1 is not equal to 0. Okay, but is this really 2 not equal to 0 or 1 not equal to 0? This is actually 2 not equal to 0 and 1x1 is not equal to 0. Okay, this is different to what we usually say, something like this. Okay, 0 not equal to 2. Okay, what we really mean is 0 times x1 plus 0 times x2 is not equal to 2. Okay, so be careful when you determine this inconsistent system. Okay, so this part is wrong. Okay, so when you swap 2, of course 2 is not equal to 0 and 0 not equal to 2, but be careful, you know where these 2 and 0 come from. Okay, it's not really 2 not equal to 0. It's actually 2x2 is not equal to 0. Okay, 2 times x2 is not equal to 0, 1 times x1 is not equal to 0. Okay, so actually there's a secret variables here. Okay, make sense? Okay, so yeah, so let me mention some top scorer here. So about 24 and 25. So one of you is Zheng Fanghao, right? Zheng Fanghao. And then Cheng Wan Fu Wei, okay, my previous class. Fu Jingrui, Zhuang Fu Wei is here. Eh, where's Cheng Wan Fu Wei? Today not here, okay. Sleep at home. Oh, here. Eh, oh, okay, I see different people. Okay, Zhuang Fu Wei here. And then Liu Hanling here. And then Wan Ye here. Wan Ye very attentive in class. Every time give me feedback one. Danzhou here. Raymond also. And then 继承豪 is who is 继承豪? Okay, 继承豪. And then 林星辰 who is 林星辰? 星辰 here, yeah. 刘云豪 here, not here. 刘云豪. 罗英杰 the back, still at the back. 罗英杰. 许念和 here. 杨清雅 there, okay, good. Okay, that's all. So, please work hard. We still have three more weeks to go before final. You still can improve your marks. Come find me if you have any problems. Okay, email me or quiz hour. So before you back, please pass me back your quiz paper. Yeah. Oh, by the way, hello. If you found any miscalculation, right, you should come back to me.
19
算错了。
39
没很重要。OK， 好，我会改。Yeah， 找一下谁是端天赐。对，
我帮他拿了。
然后你帮他拿。
对，
他没有来上课。
他前2天好像也来。
他前2天有来。
我今天好像来了，然后走了。
哦，走了。
啊。
哦，你下次告诉我一下他是谁。等于0，它就 inconsistent。
不一定啊，这个
如果不等于0的话，它就所有都有 pivot， 有 pivot 的话，它只有 trivial solution。
就是这个不一定啊，为什么不一定只有 trivial solution？这其实刚好是都是0，它是不是就是要看一下子？
没有，因为在 homogeneous equation 里面 ，homogeneous system 里面，你这边是不会变的。homogeneous system 里面，
对啊，
其实
如果这个不是0的话，那它这个不是0的时候也会有。
对，所以这个是这个 system 特别的地方，这个是 homogeneous system。
所以这个不用讨论。
所以是
不是还是要讨论一下？
哎呀妈！可以讨论，但是其实我们是假设知道的。
假设。
那
我觉得应该看一下。
其实要讨论，如果 generally 其实要讨论。因为你进行 raw reduction 的时候，这边是不会变的嘛，因为它都是0。对。
这有什么意思？
这是什么意思？
不是很懂这个题。
这个是1 to 1哦。因为你 solve， 你看你 solve homogeneous equation 啊，它的答案是 trivial solution。所以意思说它是1 to 1，因为它是 linearly independent。你记得1 to 1的意思？
老师，你把我2分加回去了。
为什么？
要不我心里不平衡。
下次我加，下次你考100分。ax 1 to 1是 ax 等于0的时候 ，if only if x 等于0。OK， bye。
哦。
Only when x 等于0。就你已经解 ax 等于0了，然后只有 x 等于0的时候，所以它就是1 to 1。
又是1 to 1，又是 on to。
这题它不 on to。
为什么？
刚才我不是解释了？
需要整理吗？
可以。但这里是没来的，这里先整理就可以了。这里边请那里整理。
按序号整理。
不需要。只是就是放正来就可以。对。它不 on to 是因为它不是每一个 pivot 都有，它不是每一个 row 都有 pivot。假设我把这一边的000换去一些 b， 一些 non-zero b 的话，它就 inconsistent 了，它就没有 solution。 onto 的定义是什么？每一个 b 我都要有一个 solution，每个 b 我都可以找到一个 x such that ax equal to b。
为什么没有 solution？
inconsistent 的话会有 solution 吗？一个 system 如果 inconsistent 的话会有 solution 吗？
但它不是以后就两个 x 吗？
对，没有错。但是你有一个不符合条件的 equation 出现，听不懂？啊、让我暂停一下。